And you've all got your calories and nutrition, and so you can stay awake for the next hour because we have a really exciting colloquium. This is Jennifer Lee, who's an astrophysicist here at Smithsonian. She started out at Swarthmore and then received her PhD from Ohio State University. She came to Harvard as a Sagan Fellow, and after that, on an open, wide-ranging search, was made a Smithsonian federal employee. And she's been incredibly active working in a very specialized area, looking for exoplanets by microlensing. And she is the deputy science PI for the Korea Microlensing Telescope Network. I think I've got all the initials right. And is also very heavily involved in planning for the Roman Space Telescope on the galactic exoplanet surveys. So we're delighted to hear about, you lost your title, but I have it written down here, the Microlensing Planet Landscape on the eve of Roman. So Jennifer?
Okay, thank you, Andrea. Right, I was just making sure my audio was off on the laptop to avoid scary reverb. You can all hear me okay? All right, great. Well, I'm very happy to be here, and thank you all for coming. I get to tell you today about the research I've been doing over the past few years on microlensing planet detections. And I think this plot sort of sums up why this is interesting. This is a plot of mass versus semi-major axis, and it's showing the thousands of planets that have been detected by radial velocity and direct imaging. And it's really great that there's thousands of planets, but you can also see that this plot has a big fat hole in it. And this is where microlensing lives. So what is microlensing? Well, let's say we have a source star, and it's in the bulge. This top panel here is a face-on view of the system as you would see it on the sky. And normally a star just sits there. It sits there emitting light, and it emits a constant amount of light, in many cases, as a function of time. And so the bottom panel shows the measured light over time in days. And the dotted line here is the baseline magnitude. So normally it would be constant. But then we can consider, well, maybe we'll put a lens star in front of the source star. And the result of that lens star is that the light from the source gets split into two separate images. And the total area of these images is larger than the area of the source by itself, and so you see a slight increase in the flux in the bottom. And I've also drawn here the dashed line, which is the Einstein ring. And that sets the fundamental scale of the microlensing event. And so the Einstein ring, its radius, depends on the mass of the lens, the distance to the lens, and also the distance to the source star. And so because the sources are in the bulge, they're at 8 kiloparsecs. The lenses are somewhere between there. And they're all M dwarfs-ish because M dwarfs are the most numerous stars in the galaxy. What this works out to be is that a typical Einstein radius is about half a milliarcsecond. And in the lens plane, this is about 1 to 3 AU, which is right in this magic empty box from radial velocity in transits. And so then we can consider, okay, let's put a planet around our lens. And in the inset here, I'm showing just a zoom of the area just around the planet. Not much is happening here. The planet is very small compared to the star. It's far from the source star. It's far from the images, so it's not doing much. You don't see any real change in the observed brightness of the source yet. And then the dotted line here shows the path that this system is going to take across the sky. And so as the lens star approaches the source star, the images grow and move, and you get a further increase in brightness. And maybe you start taking some data with telescopes, and you measure this brightness, so you get some data in the bottom panel. And when the lens and the source star are closest together, that's when you get the peak brightness of the stellar event. You can see the images are quite large and extended at this time. And then as the lens moves away, you start to see a decrease in the brightness. But you can also see in the little inset here that one of the images is starting to get close to the planet. And that's very interesting because when the image passes near or over the position of the planet, you get this additional distortion of that image, which gives you this big signal that allows you to detect the planet. And then the lens will keep moving away, the planet moves away from the images, the whole thing goes back to baseline. And so that, in a nutshell, tells you how the microlensing technique works. And the real key here is that the image has to pass near the planet in order to produce a detectable signal. And because the images are largest near the Einstein ring, it's easiest to detect planets near the Einstein ring. The Einstein ring is 1 to 3 AU, so that's where we're going to detect our planets, between 1 and 3 AU, modulo a factor of 2, because astronomers. And then in the bottom panel, if you look at the whole signal that you're seeing, there's two components. The first component is this stellar signal, which is the whole event, which lasts tens or hundreds of days. And then you have this shorter duration planetary signal, which can last a few days or as short as a few hours. And that tells you the cadence at which you need to observe your microlensing events, right? You need to get things every day in order to get the stellar event. But actually, you need to get things multiple times per day in order to capture these planetary signals. And then your Einstein radius is 0.5 milliarcsecond. These two stars, they're not orbiting each other. They're just kind of like out there in the galaxy. But they have to be within 0.5 milliarcsecond of each other to produce a microlensing signal. So you have to monitor millions of stars at a cadence of several times per night in order to detect microlensing planets and get their planets. And so I've been working with the Korea Microlensing Telescope Network, which is a ground-based network. It's got 3 telescopes, one in South Africa, one in Australia, and one in Chile. And because of that, because there's 3 sites and that they're distributed longitudinally in the south, you can get continuous observations of the galactic bulge during peak galactic bulge season. It also, each one of these telescopes has a really big camera. And so the cameras are 2.2 degrees on a side. And there's 4 giant chips. And then the this big picture here on the right is just a little sub area of one of those chips. So there are millions of stars in each of these images. And a few of those stars are doing some microlensing thing. And then using this camera, KMTNet is surveying about 100 square degrees in the bulge. In the core fields, those are in purple. There's actually 2 offset pointings to cover those gaps between the CCD chips. And they end up with an effective cadence of about once every 15 minutes. And that's good enough to detect super-Earths. And then the other fields are of progressively lower cadences, and that's roughly corresponds to progressively larger planets that you can characterize, but there's a lot of mush in there because there's a lot of distributions that go into this. So just because it's nominally only Jupiter is out in the orange fields doesn't mean you can't detect smaller planets. It just depends on the specific circumstances. And this survey has been going on since 2015. And a lot of people have worked on this analysis. These are the members of the KMTNet science team. And we've all been working so hard for the past 10 years analyzing this deluge of data from this project. And in addition to the people who have pictures here, there's a whole nother layer of operations people who keep these telescopes running and get the data down, get the data processed and all of that. And so there's a huge team of people working on this. So I don't want to suggest that this is all mine. I'm here as Deputy Science PI of KMTNet representing the project. And so we have detected planets, which is great. So the thing that I've been using as an example is a real KMTNet planet. The top panel is that whole light curve with the perturbation. The bottom shows just the perturbation, which is lasting for like 3 or 4 days. And it has all this beautiful structure in it that you can see from the KMTNet observations. And because this is a fairly long duration perturbation, the planet is fairly massive. And so the primary things we're measuring about this are the mass ratio between the planet and the host star, which is 10 to the minus 3.3, so somewhat smaller than Jupiter. And the separation scaled to the Einstein radius, right? It's about the images. Where are the images? The the images, where are the images relative to the Einstein ring? That sets whether or not you detect them. And so that's fundamentally what you're measuring about the planet, is where the image is relative to the Einstein ring. So it's 1.2 Einstein radii. And then the Einstein radius is sort of between 1 and 3 AU. And so therefore, this is the planet's at about 2.2 AU, and it has a mass of about 40 Earth masses. There's a lot of different kinds of signals that you can see for microlensing planets. You know, that was a bump. The one on the left here is a bump. The one on the right here, though, is a dip. And that's a situation in which the image is actually being disrupted by the presence of the planet rather than enhanced. And so you can also get these negative signals in microlensing in addition to the positive ones. And with KMTNet, you know, we're getting to shorter and shorter duration planetary signals. The one on the left is less than a day. The one on the right is only 1.5 days. Both of these planets have mass ratios of less than 10 to the minus 4. So they're smaller than, they're starting to get into the Neptune to Sun regime in terms of mass ratio. You can get this little tiny spiky guy at the top. This duration is only 6 hours. And the planet perturbation is minus log Q of mass ratio of minus 4.7. And so to really understand the context of the effect that KMTNet has had on the field, you have to understand where we were before KMTNet. So prior to KMTNet, it's 2014, there are 30 total known microlensing planets. And this is their little histogram in magenta. And there's only a handful of them that are known with mass ratios smaller than 10 to the minus 4. Just a few. And so the first year KMTNet commissions, not much happens. In 2016, we published the first observations, or the first planets from the survey. And so the upper left here tells you what year it is now in black, the number of planets getting published in this year, which is 2, the total number of planets on the right that are known from KMTNet. And then the legend is telling you what year those planets are from, the total number of planets and what year they're from. So this first year, 2016, we published 2 planets. The data were taken in 2015. 2017, we published 4 planets based on data taken in 2016. In 2019, there's 13 planets, distracted by this, okay. In 2018, there's 13 planets, and they're coming from a variety of the previous seasons, so the numbers are going up in all of these things. In 2019, we break even with the total previous known detections. 2020 was 2020. It was rough in a lot of ways. But something that happened in 2020 was that Wei Cheng, who is now a CFA fellow, but at the time was a graduate student, came up with this idea for an anomaly finder to automatically find planetary signals in the KMTNet data. And so the left panel here is an example of the output from his anomaly finder. So the top panel is the full microlensing light curve that's been fit with a point lens. The bottom panel is the residuals to that light curve. And what he did was he fit the residuals to that light curve with a microlensing signal, which is hilarious because planets don't actually look like plain, ordinary microlensing signals. And sometimes they're the other way around. But just as long as you allow the microlensing signal to be upside down, it works great. And so from that, he found like a whole slew of new planets. And in particular, this has really contributed to the discovery of the shorter timescale perturbations and the smaller planets and the more subtle signals. And so since that time, we've been systematically working our way through the KMTNet database and systematically analyzing all of the planets to form a complete sample. And so Ingu, who's a postdoc here, has been working on that. This is just a sampling of planets from one of his papers of all like the different little signals that he's characterized. And so in 2020, we have 49 planets, and there were 19 planets done in 2020. In 2021, there's 21 planets, right? And this is when we're really starting to do the systematic work. So we get a big jump. 48 planets get published in 2022, and 36 in 2023, and we got about 30 in 2024. And so there's been 2 really big sea changes in microlensing. First, with the start of KMTNet, which allowed you to start detecting planets en masse, and then with this anomaly finder, which allowed us to find the planets we had detected. and get them analyzed and published. And so now we have this huge sample of almost 200 microlensing planets. I didn't try to track down the things from this year. And there's a really big sample of them that's below the -4, right? And so we're pushing like an order of magnitude smaller in terms of mass ratio than we were before. And you can also see that impact on this mass semi-major axis diagram, radial velocity and transiting planets, microlensing planets in the box, all right? So these planets are really important to complement the population of planets from radial velocity and transits in terms of just completing the planet population and really finding the planets. But of course, every time I find a planet, and I would tell Margaret Keller that I had found a planet or something, she'd ask me what's up, and she would say, so? And so that's been the really exciting part of the past few years is getting into the so, right? Not just I found a planet, but what does that planet mean? And so what we've been working on is doing frequency analysis. So this is the mass distribution of a fixed sample from the KMTNet project. And so we first did 2018 and 2019 and got a complete sample of everything from those 2 years. And then things were looking a little weak down below -4 because smaller planets are harder to find. And so we also added the 2016 and 2017 samples in there. And so we get this nice distribution of the detected planets. And then Young-gil at KASI, the Korea Astronomy and Space Science Institute, did the frequency analysis, the sensitivity analysis, and it's a function, but basically small planets are harder to find, and therefore each small planet represents a whole bunch of planets in the population. And so when you correct your detections by the sensitivity, you get this increasing mass function. And so there are many more small planets than there are large planets. And you can fit this with a power law. Power law is okay. It has a power law index of about 0.6 or minus 0.6, depending on whether or not you're putting your minus sign in there. And that's great. So there's more smaller planets than bigger planets. But if you actually look at the binned predictions for the power law index compared to the actual detections, the detections are in cyan, and then the predictions in each bin are in black. You can see it's not matching very well at the high mass ratio end. And in particular, it predicts many more planets in the highest mass ratio bin than you observe. It predicts more planets than you expect in the lowest mass ratio bin. There's only one, you'd expect like 4. And then also, just below 10 to the minus 3, there's also an underabundance of observed planets. There's a deficit relative to what you would get from this solid single power law. And that's kind of interesting. And so what we found was actually you can fit this much better with a double quadratic than you can with a single power law. And that captures those two main features, the deficit at the high and the low mass ratio ends, and this bump in the middle. And the bump in the middle, this is in log space, so the Poisson uncertainties don't really, it's hard to interpret. But there's a dip in the middle. It's much better fit by the pink line than the black line. Let's go with that. There's statistics elsewhere about this. And that's really intriguing to me, because when I saw that, I thought, oh, that's interesting, because that's like right, just smaller than Jupiter in terms of giant planets. And that's interesting because that's kind of where you expect things to pile up if you have a core accretion theory of planet formation, right? So the basic concept between core accretion theory hasn't really changed since the 1980s. It's changed a lot in detail, but the basic idea is that you build planets very quickly, you grow them with solids, but then they sort of plateau for a while in terms of mass until they overcome hydrostatic equilibrium and you can get runaway gas accretion. And the result of a plateau, any kind of plateau in a time scale, is that you're going to get a pile up in mass at that range. And so you would expect things to sort of pile up around somewhere between 10 and 30 Jupiter masses, or Earth masses, 10 and 30 Earth masses, which is in the sort of 10 to the minus 4 range of mass ratios. And so then you would naturally get a deficit in between things that haven't undergone runaway gas accretion and things that have undergone runaway gas accretion on the left and right. And so this kind of structure is somewhat, the structure that we see is reminiscent of what you might expect. And so it shows the power of the fact that we have enough detections now that you're starting to see structure that you can use to start asking questions about, well, what does that mean for planet formation theory? And are these things consistent? And so then, okay. So that's bound planets. Interesting thing, fun fact about microlensing planets is that you don't actually need a host star in order to detect a planet. Everything about microlensing is about the Einstein radius. The Einstein radius depends on mass. If it has mass, you can detect it. It doesn't have to have light. And so if you just have a very low mass object, like say a free-floating Jupiter, it just has a small Einstein radius. And that means it has a short time scale when you observe it, but you still get those signals. So this is an example of what a free-floating Jupiter light curve might look like. And on the left, we have what happens if you assume that the source is a point source. And on the right, you can see the light curve if you assume that the source is actually a star, and it has some finite extent. Maybe it's a giant star. Those things are big. What you have here is a case where the planet is actually transiting across the face of this giant star. And because of the distance, you don't get a dip, you get a microlensing. And what that does is it creates this rounding in the light curve, which one, makes it a little harder to detect because the overall magnitude is down. But two, this rounding, if you can say, well, okay, so it's a giant star. Giant stars have an angular radius of 5 micro-arcseconds. Therefore, this scale here is all in Einstein radii. I can reconstruct the size of the Einstein radius from measuring this finite source effect and get a better handle on what the mass of this planet or this lensing object should be. And so from KMTNet data, we had about 30 finite source events. And from that, you can measure a distribution of Einstein radii. And so your stars are here, this orange thing, those are stars, right? Smaller things, smaller stars, also faster moving things. But it's a smooth distribution. And it's smooth because the distribution of stars is smooth. But then there's this kind of non-smoothness down at the small end. There's a break, and then you get another little collection of objects, which would correspond to planets. So it seems like there's a signature here where you're seeing two different populations of objects, one with very small Einstein radii corresponding to planets, and then your regular standard thing for stars that as you would expect. And if you just focus on the lower left corner of this, and you try to fit this population of planets, we fit it with a power law distribution. From the bound planets, we have a power law distribution with an index of 0.6, and that's in the magenta line here. There are too many planets in this sort of flat zone compared to the data. And so it looks like the power law index for the free-floating planet population is steeper, closer to 1, or 0.9 or 1, compared to the bound planet population. And so from this, we can construct a mass function that goes like all the way down to into planetary masses, right? So the dashed line here is your standard Chabrier mass function. And then the dotted line is that power law distribution of planets. And the solid line is the combined distribution. And so we have this whole mass function now of isolated objects. And then the MOA, after we did this, the MOA group reanalyzed their data. And they did both a timescale and a Einstein radius distribution. And from that, they measured this magenta distribution. And what you can see about this is that the dotted lines are very similar. They have a very similar planet, free-floating planet mass function. But the dashed lines are really different. And so from the MOA microlensing data, you get many more brown dwarfs than you would predict from a standard Chabrier mass function. And I showed this to Scott Kenyon, and Scott was like, well, it'd be really interesting to know how that compares to the local universe, because Kirkpatrick did this was looking at, this complete sample of things within 10 or 20 parsecs, going all the way down into these LT dwarfs. And they have this mass function. And so we put the mass function on here. And that's consistent with what you get from the microlensing. There are many more brown dwarfs than you would predict from a Chabrier mass function. And that's good. But it's also interesting because in this region where the planet mass functions and the stellar mass functions are overlapping, this is sort of between 3, that's the dashed line, and 15, the dotted line, Jupiter masses. And so you can really see that for things in this range, you're getting a mix of things from the planetary mass function and a mix of things from the stellar mass function. And really, the stellar mass function looks like it's dominant in terms of those objects. And so if you have a lot of people like to define, you got planets stop at 13 Jupiter masses, because that's the deuterium burning limit. Brown dwarfs, they go up to 80 Jupiter masses, because that's the hydrogen burning limit, and then you have stars. But this is really saying that, well, actually, there's 2 populations of things in this, this range right here, down about 20 Jupiter masses. It's real mushy, whether you think things are planets or things are stars. And, oh yeah, there's a caveat. Okay, so the caveat is we've been thinking about the situation. We got a planet, it's going across our star, okay? That produces a nice free-floating planet event. The caveat is this planet doesn't have to be by itself. This planet can have a host star. It just has to be far away. And if the host star is far away, it doesn't produce a microlensing signal. And then also the host star is like a dwarf, and the source star is a giant, so you can't even tell it's there because you've just got all this light from the giant. And that seems bad, because you don't know if they're actually free-floating or wide orbit. But I was thinking about this, and I realized something, which is that regardless of whether or not these planets are actually free-floating or wide orbit, the number of planets is finite. So you can put them all around host stars. But if you put them all around host stars, then there are none of them that are free-floating. Or you can say they're all free-floating, in which case none of them are around host stars. So if all these things are truly free-floating, you can't have planets around host stars at greater than 10 AU. And then at the CFA, we hear a lot about D-sharp. And we have all these beautiful disks from Sean Andrews' project, and these disks have gaps. And then people started telling me that there's planets in these gaps. And maybe these planets are like a Saturn mass planet, and that's what makes the gap. And when I looked at those, I was like, oh, well, you know what? Those planets would show up as free-floating planets in the microlensing distribution. And so then you can ask, well, okay, so are these planets proposed for these disks consistent with what you would expect given the limits from the microlensing free-floating planet distribution? And this has been the subject of something that I've been working on with Scott Kenyon. So I said this, I mentioned this to Scott, and Scott was like, well, here's a paper in which they did this. And so we have Zhang et al. 2018, where they did hydrodynamical simulations. They stuck a planet in each of one of the gaps in the D-sharp disks and said, well, what's the mass of those planets? And then if you take those planets and you make a mass function and a distribution of masses, you get these gray things. So we have the frequency of planets in each of these bins. So the bins are unevenly sized because they're binned in familiar units as opposed to even units. So we've got an Earth mass, a Neptune mass, a Saturn mass, Jupiter, and then 13 Jupiters. And you can compare that to the microlensing planets, which are in pink. And so at the low mass end, there are fewer planets predicted than there are microlensing planets. And that's just fine, because some of those microlensing planets can just be free-floating whatever's got ejected from the inner solar system, and that's cool. But once you get to a Saturn mass, the numbers of planets you predict from the simulation exceeds the amounts for microlensing, and that's bad. There are many other studies of debris disks, or of these gaps in ALMA disks. So Lodato used Hill radius. It's much more simple scaling rather than hydrodynamical simulations, but they find this, and they still find too many Saturn mass planets. Wang did a more sophisticated version of this. And then Zhang did a bigger, the torus sample in addition to the D-sharp sample. And the bottom line with all of this is there's too many. And so there's too many. There's more than you get from the microlensing free-floating planet population. And so that means one of two things. One solution would be that only things that have ALMA disks with gaps have planets of this mass. And that helps because, you might say only I think there's an estimate in Lodato that there's 35% of stars have disks with gaps. And so that gets you a factor of 3, but it's still pushing some tension with the microlensing values. A factor of 3 doesn't entirely save you here. And it also requires that all of the microlensing free-floating planets are bound, or that those things get stripped off and ejected later, but they're all related. There's no spares. Or you could just say, well, maybe not every ALMA gap has a single planet in it. And that seems a more plausible explanation to me. And there are examples where you get where people have simulated disks where you get multiple gaps from a single planet. And so that's a potential explanation. Then there's a lot of other measurements or predictions of wide orbit planets. So this is extending our semi-major axis out to 1,000 AU and up another order of magnitude in mass. And out beyond 10 AU, we get we get planets from radial velocity, and we also get planets from direct imaging. And then the people who are doing those studies have also made measurements of what is the frequency of planets. So for example, we have Nielsen et al. Looked at the GPIES survey and made a prediction of how many 5 to 13 Jupiter mass planets there should be about beyond 10 AU. And they have their mass function here. And the answer is too many. This is the microlensing limit for the free-floating planets in the dotted line. And this is the limit, like the total limit of all things. And they're kind of, they're a little close. You don't really want all microlensing brown dwarfs and planets to be bound to stars. You do find brown dwarf objects, like the things in, what is that, Sigma Orionis. They're finding these cores that are 10 Jupiter masses by themselves. So you can form brown dwarfs, it looks like, at these small masses. So you don't want them all bound to planets. The good news is that the GPIES survey, really, they only find their planets around the highest mass stars. And there aren't very many of the highest mass stars. And so if you say, well, actually, you're only finding these planets around the highest mass stars and not all stars, then you can divide by a much bigger denominator of what is all stars. And there are fewer planets per star. It does mean you can't have planets around those other stars. But the numbers come into better agreement with the microlensing. It's not like impossible. But I think there's still a suggestion here that a bunch of these things that you're picking up in direct imaging at like 13 Jupiter masses are actually what we would consider brown dwarfs and from the tail of the stellar mass function rather than being planets. Ooh, those terms are so mushy. Ugh. Okay, anyways. You also have this other study from Vegan, and what's interesting about them is they do consider this idea that what they're observing is a mix of brown dwarf and planetary populations. And so they measure like a total frequency of everything, and then they break it down into the brown dwarfs in blue and the planets in green. And those numbers are okay with the microlensing as long as you let some of them be brown dwarfs. So you want to let some of these imaging objects be brown dwarfs. I think this is over a much wider range of masses. It's going up to 75 Jupiter masses. So, those things are starting to plausibly be brown dwarfs, but you're thinking more about like high mass ratio binaries rather than star-planet systems. With radial velocities, there was a work by Fulton where they were measuring the number of planets out beyond 10 AU. And again, they're massive things. They're 1 to 20 Jupiter masses. But where their frequency it's right on the edge of what's allowed by the microlensing. And you see that for this sample, and also if you restrict it to just the 5 to 13 Jupiter mass objects, again, you're starting to, it's like almost there, but again, so there's the two things. One thing is that it only kind of works, and then two, under the scenario, you have to make all of those microlensing objects bound. They all have to have stars. The one good thing about this, the one thing that turns out to be maybe our saving grace, is that Fulton et al. Say that they're doing FGKM stars. And that's bad because that's basically all stars, and so there's no correction factor for your hosts. But when I was thinking about this, what I realized is that at 10 AU, the period of your planet for an M dwarf is very different from the period of your planet for a more massive star. And that's our saving grace here, because if you divide the duration of observations, which is basically uniform across their sample, by the period, then you're covering a much smaller fraction of the periods for the lowest mass things, or the lowest mass host stars. And so these are all of the points, the blue points are everything in their sample. The magenta points are the things where they're detecting these long period planets, and they don't have good completeness out here, and, which they did talk about in their paper, but the thing they didn't talk about is the fact that their completeness is a function of spectral type or mass, which logically makes sense, but that's good because it means there's not really M dwarfs in there. And as long as M dwarfs don't have planets, then you have this big denominator you can add, because all stars are M dwarfs, and you can get all the fractions to work out, and it's not so terrible. All right, and then last, Scott Kenyon loves debris disks, so we did debris disks too. And this is saying Pierce et al. Calculated the minimum mass planet required to sculpt the inner edge of the debris disk with a single planet. And the black line is the full distribution of masses from their sample. And then the colored lines are broken down by spectral type bins, or mass bins. And there's only 4, they cover all masses, but there's only 4 M dwarfs in their sample, so there's some squish in that part. And then the fact that the colored lines are sort of sequential in rainbow order reflects the fact that more massive host stars require more massive minimum mass planets to sculpt the disk, the debris disk. But if you normalize by the median value, they all have about the same shape. And that shape, we can test that against this power law index. So for microlensing, we have the power law index of 1, and 1 is the gray line here. And that produces too many big planets. So the power law index corresponding to this Pierce distribution of planets is much shallower. And that's okay as long as it's shallower because it has fewer small things, right? Because you can just have, microlensing can just have a whole bunch of free-floating Earths or Neptunes or whatever, and then everything works out fine. And so the question is, are they consistent when you do the frequencies too? And the answer is, yeah, kinda. So this is our frequency in microlensing is the magenta. And there's way more microlensing things in the smallest mass bin than there are objects in this distribution, and that's fine. But if you assume that the debris disk planets are representative of all planets, then you get the solid black points. And those ones, they match the microlensing, which is good. It means it's not illegal, right? But it does, again, require all those microlensing planets to be bound. But you can think of it also as a lower limit. Let's say that only things with debris disks have planets that are a Saturn mass or larger. Then those numbers go down, and now some of the microlensing ones can be free-floating, but you can't have things without debris disks also have planets. So there's a lot of different ways to look at all of these numbers and try to fit them together into a single story. The other thing about this, though, is that these are all minimum masses. And so the microlensing actually sets a limit on the maximum masses because you can see, because these things are already so close, the masses can't be a whole lot more massive than they already are. You can't make them much more massive than the minimum mass, or you push the whole mass function over. And so it gives you a way to set an upper limit on the masses of things from this Pierce study. The one thing that could save you there is if instead of a single planet, you have multiple planets that sculpt the debris disk. If you have more than one planet, then all the planets can be less massive. So the gray line is the 1-to-1 line, and the magenta points are single. If you have one planet, how big does it have to be versus many planets, or planets spaced every 16 Hill radii. And that's your multiple planets. But whether or not these things work out in practice depends on how many planets you need. Because if you just calculate, I tried calculating, all right, for these things, we got one planet, it's like 10, and how many of them would there be between, if you just equally space them, between 10 and the inner disk edge? And then you get like between 3 and 10 or 17 planets per star, and then you start getting too many. But it's not clear that that's how many you're required to have, it's just how many fit with this spacing. They didn't calculate the required number. So it's not, it kind of depends on how many you need, whether or not this can save you. And so the conclusions from all of this work are that for radial velocity and direct imaging, we're generally talking about things greater than a Jupiter mass. And of that population that you're detecting with radial velocity and direct imaging, some of those are probably brown dwarfs, or all microlensing free-floating planets are actually bound to their star. Those are your two choices. With debris disks, you have a sort of similar picture, but you get down to smaller masses, right? All of these things are either bound to their stars, or only things with debris disks have planets. Things without debris disks can't have planets more massive than Saturn. Or, I mean, there's like some squish in there, but that one's a continuum. And then these things with debris disks, they're pretty close to the minimum mass. They can't be too much more massive. Or you have to push them to multiple planets to sculpt these disks. And then with ALMA disks, it really seems like you can't have all those Saturns in individual gaps. You want to produce multiple gaps with a single planet, or produce them some other way. No planets. That would be better. Either way. But there's all these different constraints and different ways of looking at all these measurements and trying to get them to fit. And so the microlensing mass functions, we've got mass functions now for both bound planets from sort of 1 to 10 AU, and it's a mass ratio function rather than a mass function. And then we have this mass function. This is actually a true mass function for just basically constraining everything outside of 10 AU. And these things are going down to super-Earth masses. And they're well constrained enough that you can start interacting them with other measurements or predictions and placing constraints on what's going on with the physics. And so that's sort of where we stand now with microlensing. And going forward, the Roman mission is going to be launching soon. And I think the thing that's really exciting about Roman is that Roman goes deeper than you can get from the ground. And that doesn't make your photometry more precise or anything. The key thing that does is it makes your source stars smaller. So when you have a giant star, it's got a big source, and then you start to wash out your microlensing signal because you're integrating it across the whole face of the giant. But when you have a dwarf star, it's a lot smaller, and so you get much more detailed structure in your planet perturbations. Your signal doesn't get washed out as much, and so it's easier to detect things because the change in brightness is bigger. And so that's the real power of Roman, is because it's going to smaller sources, it can get smaller planets. And that will allow us to push this mass function down smaller, and also let us push to smaller free-floating planets. And then, also because of the high resolution of Roman, which is similar to HST, when you measure light from the stars, you've got your light from your source. You always have your light from your source. Oh, right. And then you have your light from your lens star. And then also, again, because the sources aren't giants, you can actually, if there's 2 stars there, you can actually say, oh, well, there's 2 stars there, and not just one giant and maybe some smaller stuff and who knows. So that's the source effect. But then the resolution effect is also, it's the bulge, and there's all these stars in the bulge. And when you have all these stars together in the bulge, then they're all sitting on top of each other. And so you have your light from your source, you have your light from your lens, you have light from the companions that might be orbiting those things, and then you just have light from other stars, because there's just a lot of stars. And it makes it very hard to constrain the light that's actually coming from your lens star. But with Roman, you have higher resolution, so you can at least get rid of the other stars, which makes it easier to make a measurement or a constraint on the light from the lens star itself, also because the sources aren't giants. And that gives you a better handle on those properties, which allows you to reconstruct the planet properties better, because you need a mass you need a host mass in order to get from a mass ratio to an actual mass. And so with Roman, we should get smaller stuff, and we should also be able to transform this mass ratio function into an actual mass function for planets. And that's what I have for today. So thank you very much, and I'll take questions.
Thank Thank you, absolutely fascinating, fascinating. We have time for questions. I want to go back to the, wait a minute, I've got to do something here useful. Now it's on, there we go. I want to go back to the very, very beginning. Whose idea was it to build this Korea Microlensing Telescope Network that's so amazing?
This is a hilarious story.
How did that start?
So Chang Ho Han is a researcher in Korea. He's a professor at Chungbuk National University. And the origin of KMTNet was he went to the Korean version of NSF and said, I would like to build a microlensing telescope, you know, a telescope with a big camera so we can do a microlensing survey. It will cost you $10 million. And they said no. And so the next year, he wrote a proposal that says, I would like to build 3 microlensing telescopes with really big cameras, and it will cost you $30 million, and we'll clean up, and it will be the biggest thing ever. And they said, oh, okay.
Okay, there's a lesson there. Okay, I don't know if it works on this side of the ocean, but we admire that. Are there other comments? Yes. Mm-hmm. Oh, here, wait a minute. You've got to have this.
I'm guessing between the automated search algorithm for looking for the microlensing events and the complicated intrinsic population, it's hard to go from cyan to blue in this case. So how did you actually invert the observed distribution in log Q to the inferred one?
So the actual process is you take all the KMTNet microlensing light curves and you inject planets into them in all the spaces in the grid in all the ways, and then you ask whether or not the algorithm recovers that planetary signal. And you spend about a month on 20 computers doing this for each year, and then you get a function.
Charles, you had your hand up next.
Okay, thank you. As you know, I love microlensing. You didn't show any events where you had a star and 2 or more planets in orbit, but you have seen those, have you not?
Yes. Yes, we see those.
Where are they?
Where are they? Well, those ones, we kick them out of the statistical sample because they're too complicated. Well, if it's just 2 planets, they're allowed to be in there. But there's also things where you get 2 stars on a planet. And those ones we have to kick out because circumbinary formation or formation in a binary star system is different from when there's only 1 star. But yeah, so does that answer that?
Yes, in your turn.
I'm just curious where white dwarfs fit into these distributions. I mean, could those be hosts of some of these hostless planets, free-floating planets?
Yes. So there are, basically it's just mass, right? So it's a question of abundance versus mass. So when you see something and you see something that's 1 solar mass and you think it's 1 solar mass, then you check to see if it has light. And if it's light, that's good. And if there's no light, then it's a white dwarf. And Wei Chang actually has a project where he's looking for hosts of planets and trying to figure out, like he has a whole bunch of candidates that might have white dwarf hosts. And so he's trying to place limits on that light in order to constrain that. Yeah.
Dave, then I'll go to you.
Thank you for this talk. So I just would love to hear your thoughts about the relationship between KMTNet and Roman. They will be operating at the same time. They'll look at the same patch of the sky. What do we get from that? What are the opportunities there?
I think the opportunities there are not well defined because they're at such different magnitudes. And I looked into this, and basically, if you look at the predicted population of Roman planets and the properties of their sources and lenses, they're so faint that you don't really see them from KMTNet. And so it's tricky to have overlap there. But where you can get, like, in the cases where those things do line up, then KMTNet is valuable because it has a much longer observing season. Roman being in space, it seems good because there's no weather. But then, because the bulge and the ecliptic runs through the bulge, in order to balance the whole, my solar panels want to point at the sun, and I don't want the sun going down the barrel of my telescope, there's actually only 2-month seasons And so there's going to be these huge gaps in the Roman data, which we're hoping can be filled in with ground-based data to help characterize events because, like sort of 20 days, but then if you have one that starts sort of at the beginning or gets a wide distribution, it would be helpful to have ground-based data help constrain that. But yeah. So.
Yeah, I totally agree with the idea that not every gap has a planet in it. I think that's actually not possible hydrodynamically to make that work. But let's pretend that each planet does have, or each gap does have a planet in it. Can you use the microlensing distributions to say something, and maybe the transit and radial velocity things to say something about migration? Because the disk planets are much, much younger than the microlensing planets. Is there any limit there or no?
So this is interesting. Okay, so let's say they all have a Saturn mass planet now, but those planets go somewhere else. They can't go out because the microlensing is everything outside 10 AU. They have to go in, and then you start running into actual constrained measurements of the population. And I'm pretty sure, basically, they have to go in, and some of them have to get swallowed by the star because you have to make them go away because there's limits. Yeah, that's.
Yeah, wonderful talk, but it's been left to me to ask the nasty statistical question, your plot on the left. How did you actually determine that a quadratic was permitted? Because if those are 1 sigma error bars, then a single power law is perfectly fine. So.
Well, okay, so remember this is a log scale, and also there's a lot of things about this plot. One is that we've plotted the errors on the data where the errors are really on the model. And then it's on a log scale, and so that makes the error bars themselves somewhat misleading. This ended up in science, and so we had to do our best to make it palatable to all stripes. But it works out. It's a delta chi-square. It's like a 22.6, so it's like several sigma result. And we don't actually fit a histogram. We fit the cumulative distribution.
Okay,
with
that's
the sensitive.
basically my question.
Yeah. So we don't fit the histogram. It's just people like histograms. The general public likes histograms more than cumulative distribution functions. And the other thing about this is just a subset of the sample. And over the 2 years it took us to publish this, the sample got a lot bigger. And I think the structure is becoming more rather than less apparent.
It's a kind of follow-up on what Charles asked earlier. Have you detected any exomoons? And if yes, then how far are we from understanding the statistics on how many giant planets have them?
We have not detected any definitive exomoons. We detected one case that can be explained by an exomoon, but it can actually also be explained by just having 3 sources, one type binary with a third guy. And that sort of scenario turns out to be Occam's razor simpler than the scenario with the exomoon, because the exomoon has to be in a slightly funny place to detect it. So not yet exactly, but we could in theory.
Any more questions? Yes, Phil.
Very interesting talk. So the dip in the mass distribution is very reminiscent of the radius distribution gap that we found in the Kepler planets, right? Are these the same thing? It seems like it's a very similar argument, but I was wondering if you use some type of mass radius relationship, it would give you somewhere approximately the same thing.
So we just measure the mass ratios. The Kepler thing, though, is the physical mechanism there that explains that gap is the heating from the stars blowing off the outsides of the planet. That's one of them. There's a second one I don't recall exactly. But it's heat blowing stuff off. I think in this case, this is more of a timescale argument, right? How you get things that pile up you get stars that pile up on the main sequence and in the red clump, and there's sort of a gap because things migrate off the red clump very quickly. Because things go through runaway gas accretion very quickly, you end up with a gap between the pileup from the initial accretion of solids and the runaway gas accretion. It's just a time scale argument. And it hasn't been quantitatively tested either. I think that's, I think that this is indicative. Scott Kenyon looks at me and raises an eyebrow at me when I say these things, so,
Thank you.
yeah.
Thanks. Any more comments, questions? Well, let's thank Jennifer. That was a great talk. Appreciate it.